Hello, class. We're going to begin our discussion, or actually continue our discussion, when we are looking at the reactivity of a carbonyl compound, such as aldehydes and ketones, with a strong nucleophile. And that strong nucleophile is going to be negatively charged, typically. Okay? So a Grignard reaction is going to be a strong nucleophile, but it's not necessarily negatively charged. But when you have a strong nucleophile, we realize that it has to be under basic conditions. But with these reactions, when you have a strong nucleophile under basic conditions, you have to do a second reaction, and you have to do an aqueous workup. So you could use water, or you could add a little bit of acid, but typically it's like just an aqueous workup is good enough. So we'll just say, for the general purposes, let's just say water. Okay. So the mechanism here that I'm going to show you applies to most of the strong nucleophiles. When they see a carbonyl compound, the lone pairs on the nucleophile are going to come in and attack the carbonyl. Now, if that's the only pink arrow I draw, then what have I just made? A Texas carbon, right? So we have to make sure that we break the pi bond and put the electrons there. And now we're going to get what? We'll have our carbon here minus our nucleophile is going to attack there. And then we have our methyl groups right like that. And then now we've generated our tetrahedral center. And so the second step now comes into play. So this is step 2 now, where we have our water molecule. There's going to be a lot of water there. We're in this step now, and so the electrons come here to protonate that. And that generates our alcohol. So this is one way, or another way, to make alcohols. We take a aldehyde or a ketone, aldehyde or a ketone, and treat it with a strong nucleophile under basic conditions, and we can get ourselves a alcohol. So that's that mechanism. Now let's take a look at when the nucleophile is weak. And when the nucleophile is weak, what happens? It's typically no longer negatively charged. It's typically just neutral. And we've learned that when we have a weak nucleophile, we can't use basic conditions. It has to be acidic conditions, right? And under acidic conditions, we don't really need that aqueous workup. So what's happening here? If I take my weak nucleophile and draw the arrows like this, it all looks good. But it doesn't happen that way because this nucleophile is weak. So it's not going to attack this carbonyl like we would expect it to, because this nucleophile doesn't have enough electron density around it. It's not nucleophilic enough, hence we call it a weak nucleophile. So it's not strong enough to attack the carbonyl. So what we we can't change the nucleophile. The nucleophile is what it is. So how can we get this nucleophile to attack this carbonyl? Well, that's the cool thing. What if we could make this carbonyl carbon right here more electronegative, electropositive, or another way of saying it, electrophilic. So let's just say right now it has a partial positive about that big. Well, what if we want to make it like that big? And if it's bigger, then that nucleophile now is strong enough or is able to attack that carbonyl. So that's what the acid is going to do for us. It's going to take that carbonyl carbon and make it more electrophilic so that the weak nucleophile can attack it. So how does that happen? So when you have a weak nucleophile, the first step is it's going to take the acid. And these electrons on the oxygen right here are going to come and abstract that proton. And so now what do we have? We have a positive charge on that oxygen. I thought I was saying we needed to get a positive charge right there. Well, it does, because look, we have a resonance structure. So now we have a positive charge on that carbon right there. So what I want to compare right here is if I take this structure before it reacts with the acid, we could draw a resonance structure that looks like this. Okay? Now I want you to compare this species right here to that one. What's one of the differences? Well, this one has a negative charge. This one has a hydrogen on it, right? Well, what's the consequence of that? This is going to have a partial positive about that big, and this is going to have a much larger partial positive. So what we've done is we've just made this carbonyl carbon right here more electrophilic, so it's more reactive with our weak nucleophile. And now that we have a species that has more positive charge to it, our weak nucleophile will now come in and attack like that, giving us our product. So we would have our carbon here, OH. I'll put the nucleophile right here. Okay. Like so. Generally speaking, that's how it's going to work. Now I want to show you an example to have this make more sense. And I'm just thinking if I want to do that example now or later. So let me think about that for a second. So let's take a look at a reaction that forms a product called a hydrate. Now this is a hydrate, but it's also called a diol. And a di meaning two, and the ol means two alcohols. So when we have two alcohols, like in this conformation right here, two alcohols, well, let me take that back. Okay, for right now, I'm going to call that a diol. I'm thinking of something that's tripping me up, but I'm going to have to double check on that. But it's guaranteed fact, this is a hydrate. I'm thinking it's a diol, but I'll get back to you on that, okay? So what we have is a hydrate. What happens is when we take a very, very simple ketone or aldehyde and place it into water, equilibrium favors the hydrate. But when we get into a more complex aldehyde or complex ketone and you place it in water, the reactant is favored. So if we want a really complicated ketone to become a hydrate, we have to up the ante by putting it under basic conditions or acidic conditions. You get to choose. You can't do these at the same time, so you have to do them separately. So if we want to get that reaction to work, let's take a look at basic conditions. So what we are going to do, let's do the mechanism here. So the reaction that we are going to call this is going to be base catalyzed hydration. So this is a basic condition. So when you make water basic, what is it going to do? It's going to be a hydroxide. Let's draw that hydrogen a little closer. So under basic conditions, we're going to have a lot of hydroxide. And so what's the mechanism here? It's going to come in. So we're going to have this negatively charged, and then our OH is going to be like that. And under basic conditions, there's still going to be a lot of water here as well, correct? And so the next step is going to be the protonation step, or the proton transfer. Proton transfer. So we are going to have some water here. And so this is going to come in, grab that proton, and do our protonation step. So I'm going to draw the product right here to give myself some room. Just like that. So if we can color code this oxygen right there is that one. And then this guy is that guy. So that is the base catalyzed hydration of a ketone or aldehyde when you are using water and you make it basic. Now, what we're going to look at is the same reaction, but under acidic conditions. Now let's take a look at the same reaction now, but under acidic. So if we have our ketone and it's in water, but we've made it acidic. Under acidic conditions, the first step is the oxygen right here is electron rich, so it's going to attack that electron poor hydrogen to protonate it. So that's an equilibrium process. So we're going to have that now. And we just generated some water. So that water, that piece right there is that piece right there. Now it is positively charged there, which we previously learned now makes that carbonyl carbon more electrophilic. So now the water can come in and attack. And that process is reversible. So now what do we have here? I'm going to draw it right here so we have more room. We have OH. So the water comes in and attacks the carbonyl compound. There's our water. Now we see an oxygen with 3 bonds, so that means it has to be a positively charged species. So what we have to do is another proton transfer. And we have a lot of water floating around. So that water right here, water's acidic and it's also basic. So that's water is going to come in and grab that proton. That will dump the electrons on that oxygen. And then that gives us our product. And there is our hydrate. So when you compare the basic conditions versus the acidic conditions, we get the same product. It's just the steps are a little different. Okay? And then when this water molecule attacks that, what do we generate at the end of the day? We generate another acid molecule. Hence we say acid catalyzed. We generate our acid again. Okay, let's see if there's anything else. Okay. Now there's this guiding principle here that will help you to know if your mechanism is correct or not. Okay? So this is the correct mechanism, and now I want to draw it in with an incorrect mechanism, and I want you to see why that's so incorrect. Okay? So let's say in your mechanism here, I'm thinking here. Let me think about what I want to say. Okay. This is what I wanted to say. So let's do the acid catalyzed mechanism here, but let's do it incorrectly. So we have our acid here and we have water. Let's say a student decides to not protonate the carbonyl oxygen like they should and just draw the water coming in. Okay? Doing that. What would this intermediate be? O, H, H. That would be the original. What did we just make right here? Do you see how that's a base? It's negatively charged. You cannot generate a base under acidic conditions. It just won't form. So if you know for a fact that you are under acidic conditions and you start generating these negative charge species, then you know you've done something wrong. The mechanism doesn't allow for that. You can't have base when there's so much acid present. It just doesn't work. And the opposite would go with if you look at the basic conditions here. All right. Let's say if we have this. So what's the real mechanism? The base comes in and attacks, right? So if you generate in one of your products an acid under basic conditions, that's not possible. You're under basic conditions. You cannot generate an acid. Okay? So let's see, for example here, what if I, instead of using the hydroxide, I use the water instead? What if I did this? We would get an alkoxide, right? So that's good. That's okay. We're under basic conditions. But what did I just generate here? I generated an acid. That's a no-no. That cannot form under basic conditions. So if you see acids popping up in your mechanism, when you know you're under basic conditions, then you know you've done something wrong. That's just a good rule of thumb and a good way to make sure you know what you're doing. Okay, the next reaction that we're going to look at is very similar. So right now, what we've just learned with the hydrates, we have something that looks like this, right? There's our hydrate. The next reaction that we're going to look at is something called acetals. And acetals are simply, you just replace these hydrogens with R groups. That right there is a acetal. And then as we progress in here, we're going to differentiate between an acetal and a ketal shortly. Okay, and then we'll make sure we understand what those words mean. But overall, what we're doing is we're replacing the two hydrogens that were here in the hydrate, putting R groups. So that's the next reaction we will look at. Okay, so in general terms, if we take a ketone and we treat it with 2 moles of an alcohol. And we do this under acidic conditions. What we're going to do is tack on the alcohols, the OR part right here, like this. Okay? And your textbook calls this an acetal. I don't agree with that, because what did we start with? We started with a ketone. And then we took that ketone and put the 2 OR groups on there. So actually, this is called a ketal because it came from a ketone. Your textbook will call this an acetal. And that's just, I think, just a tradition of how people refer to these compounds. But technically, it is not an acetal. It is a ketal. But your book will use it interchangeably, okay? So what would an actual acetal look like? Well, you can probably already guess what's going to happen. If you start with an aldehyde, use 2 moles of alcohol under acidic conditions, you will then get our acetal. All right. So that's what I want you to know, but your book just lumps it all together as acetals. But this is really what it's supposed to be. Okay, so we are going to look at the mechanism of these acetals and how they form. But hopefully we can see here, do you see how we have this oxygen here? It is now no longer here. It's because these 2 oxygens right here came from the alcohol. So this guy went away. And doing the mechanism is going to help us understand where that oxygen went to.